The objective of dielectric measurements is to study the dielectric properties of reinforced concrete structures, concrete and byproducts of rebar corrosion for 1. Data interpretation in slimming gears, and 2. For numerical simulation of GPR inspection. In this video, you can see how the analyst is calibrating the network analyzer along with a coaxial probe that we are utilizing for taking the dielectric measurements. The equipment we are using is an Agilent E5071C network analyzer, which has a range of 0.1 MHz to 4.5 GHz. Measures the dielectric property of frequency, and we can get the complex electric permittivity from the material. The coaxial probe kit that you can see here is an 85070E, which has a frequency range from 500 MHz to 50 GHz. The way that the probe kit operates is that the EM wave penetrates into the material under testing and detects the reflected signal. The important thing to remember is to try to avoid an air gap at the interface of the material under test and the probe. Because the relative dielectric constant of air is just 1, the results may suffer from the air gap. The attempt of this experiment is to try to eliminate the air gap as much as we can. So now I'm going to present to you our acceleration corrosion experiment in UMS Low. The objective of this acceleration corrosion experiment is to induce corrosion on the steel rebars in the reinforced concrete slabs in order to assess the corrosion level in reinforced concrete slabs using radar and other non-destructive testing methods. For our reinforced concrete, for our slabs, we were able to cast 4 slabs. Each slab is 6 feet by 4 feet, and it's 7 inches deep. Slab 1 and slab 2 have two rows of rebar. One at 1.5 inches from depth, and the other one at 2 inches from depth. Slab number 3 and slab number 4 have the same exact rebar depth, and they have 3 different rebar depths: 1.5, 2, and 2.5. Slab number 3, again in slab number 4, are exactly the same, except that slab number 4 is the control slab, and slab number 3 is subjected to ponding. The ponding solution that we have been using is 15% sodium chloride solution by concentration. The ponding begins on Friday afternoon and ends next Tuesday after that. So there is a 4-day wet cycle and a 3-day dry cycle. The 4-day wet cycle, the ponds are subjected to 50% relative humidity and a 90-degree Fahrenheit temperature that is controlled by this blue tarp that you see in the top. While in the curing period, in the dry period, the slabs are cured by a 72-degree Fahrenheit and also by a 50% relative humidity ambient. The way that the ponding works, the chloride ions will be introduced into reinforced concrete slab that will then destroy the coating of the rebar. After the protective coating is destroyed, the corrosion will be initiated, and this essentially is an overview of the mechanism of corrosion. Other tests that we plan to run on the reinforced concrete slabs in the future will be macrocell test, and also external current will be applied to slab number 3 in order to even accelerate more the corrosion process. Slabs 1 and 2 will stay only with the ponding, and slab number 3 will have ponding and external current applied to it. The objective of half-cell potential measurements is to correlate the half-cell potential measurement with the measurement taken using other electromagnetic wave equipment, something like GPR, gears, and to see how these electromagnetic wave equipment works to detect corrosion. Because half cell potential has an ASTM standard and other electromagnetic methods do not, we have chosen this to have the most accurate description of whether or not there is any probability of corrosion. To study the likelihood of the corrosion in the reinforced concrete slabs. The equipment we are using is a 331 MK2SH cover meter and a half cell reference electrode from Elco meter. The reference electrode that we are seeing in this video is a silver chloride reference electrode. Based on ASTM C876, which is the standard that dictates how we take the half cell potential measurements, first we are supposed to wet the surface of the slab at least 1 day before taking the measurements of the reinforced concrete slab. We would connect a red wire coming out of the reference electrode with the rebar that you see here in the picture in the top node, and the black line with the reference electrode that you see in Alice's right hand. If we have a fluctuation of plus or minus 20 millivolts in the measurements from the half cell potentials, we should not use the data. Conversely, if our data does not range less than 20 millivolts, the data is good to use. One note to keep is that on this video we are using a silver chloride reference electrode. The ASTM C876 standards requires us to use a copper sulfate reference electrode. However, we had some issues with the copper sulfate reference electrode, which essentially made us to use silver chloride reference electrode. However, this should not be an issue to us because all we have to do is transfer the potential from the silver chloride reference electrode to the copper sulfate reference electrode potentials, and we should be able to achieve the same reading as the ASTM C876 standard.